This will be the first of probably three videos on gases. Okay, so the first thing we're going to talk about, the nature of gas pressure. So when we talk about pressure, we're talking about force being applied over a given area. So force divided by area equals pressure. So how does that apply to us? If somebody comes up behind you and slaps you on your back with their palm, it's probably not going to hurt. It's probably not going to be a big deal. You'll probably enjoy it. It'll probably be like attaboy kind of thing. But if they come up behind you and they poke you with their index finger, that's probably going to elicit what are you doing? Even though the force is the same, the area is not the same. The area is much smaller, and so that force being applied over a smaller area causes the pressure to be higher. Another way to think about that is if let's say I'm laying on the ground and my daughter walks on me. Let's say she's wearing regular tennis shoes. She only weighs like 52 pounds, so it's not a big deal. But what if she changes her shoes and puts on her soccer cleats and then steps on me? Her weight is now not distributed over the soles of her shoes, but over the cleats. And so that becomes much more painful. If a woman wearing high heels were to step on your toe with the high heel part, they could easily break a toe. They could easily punch through like tennis shoes. Okay, so pressure is about force being applied over the area. So now let's go back to what we were talking about, which is the nature of gas pressure. How does this concept of P equals F divided by A equal to gases? Okay, right now you are being pummeled with gas particles, nitrogen and oxygen for the most part. I mean, literally pummeled. Billions upon billions upon billions of these molecules are running into every portion of your body at hundreds of miles an hour. No joke. You have nitrogen molecules slamming into your eyeball at 300 plus miles an hour. Why are you not feeling that? We'll come back to that. But the important thing to understand is your body is the area and the force is the speed at which the particles are coming at you. Okay, so if you were to have more particles coming at you or particles coming at you faster, then those particles would impart more pressure on you. Alrighty, so I want you to think about a column of air, like this is you down here on the surface of the earth, and there's a column of air over the top of you, and all of that is coming down on top of you, providing you force. The atmosphere is nominally about 100 miles thick, but most of the atmosphere is within the first mile, mostly within the first half mile, actually. And the pressure that this column of air over the top of you equates to is 14.7 psi, or pounds per square inch. Pounds per square inch. So pounds is a measure of force, and inches squared is an area. So imagine you've got 1 inch. So I don't know, take like a Post-it note and cut it up into a 1 inch square, and then set that down and imagine a 15-pound weight situated on top of that 1 inch square. That is what is being applied to every square inch of your body. 15 pounds, well, 14.7 pounds for every one of those square inches. How is it that you're able to withstand that? The answer is you have 14.7 psi inside your body right now, pushing out. Imagine a door that swings both directions. You see these in restaurants sometimes. If somebody is coming out of the kitchen into the dining room and somebody's going into the kitchen from the dining room at exactly the same time, and they're exactly the same size and they push with exactly the same force, the door won't go anywhere. Even though lots of force is being applied to the door, the forces cancel each other out and nothing happens. And that's what's happening with you right now. Even though the gas particles are beating the heck out of your face, your skin, every portion of your body, the inside of your body is pushing just as hard. So then it doesn't move. What happens if those forces aren't equal to each other? If you go up to Mount Hood, You feel that. When I drive up to our house at Parkdale, I feel that. When I go from the river all the way up to here, my ears pop. So what's going on with ear popping? Really, the situation is, let me get myself some space here. You have an eardrum, and then there's, let's say this is your head. There's a certain amount of pressure in here. And then there's a certain amount of pressure out here. And under normal circumstances, those pressures are equal to each other. Well, what happens if you start to drive up Mount Hood? Then the inside pressure becomes greater than the outside pressure, and then this eardrum bows out. And that can be uncomfortable. For some people, it can be debilitating in the amount of pain that it generates. And then what happens when you come down the mountain? The exact opposite. Then the exterior pressure pushes the eardrum in, and you need to increase this internal pressure. So you do that simply by breathing or sneezing, plugging your nose and blowing. Lots of different ways that you can equalize that sinus pressure inside of your body to make sure that the pressures are equal or not. This is applicable to diving. So the interesting part about pressure is it takes about 100 miles of air over the top of you to equal 1 atmosphere of pressure, which is 14.7 psi. But if I'm talking about water, obviously it doesn't have to be that far. So here's the surface of my water. All I need to do is go down 33 feet. If I go down 33 feet, I have twice as much pressure on me. My body will now be experiencing 29.6 psi. That's a lot of pressure. Imagine yourself diving down to the bottom of a 10-foot swimming pool. That doesn't feel good on your ears. 12 foot doesn't feel good. 15 foot doesn't feel good. 33 feet, it would be painful for you to just dive down 33 feet. So how do scuba divers go down 100 feet? They go down, they wait, they breathe, then they go down, they wait, they breathe. What is this process doing? You actually inhale and keep more air than you exhale. So let's say you breathe in 4 liters of air. You only breathe out 3.5 liters. Well, what happened to that half liter? It is now dissolved in your bloodstream, pushing out to equalize the force that now the ocean is pushing in. So if you do this slowly, you will end up having an internal pressure a lot higher than normal, but is equal to the external pressure that the ocean is now applying to you. So you can withstand being down 100 feet. What's important about scuba diving is realizing that if it took you a half an hour to get to the depth that you're diving at, it will take you a half an hour to get to the surface, or you can have severe problems like gases being formed in your bloodstream. That's a terrible idea, because what if that gas blocks a capillary in your brain that is the section of your brain that memorizes fractions? Now all of a sudden you can't do fractions, or speech, or your vision is gone, or it pops and you have an aneurysm and just die. There are lots of bad things about surfacing from a deep depth scuba diving if you do it rapidly. So when you do it correctly, you elevate to a certain level, stop, and breathe. And what you're doing now is you breathe in your 4 liters and now you breathe out 4.5 liters. And so you're getting rid of that gas as your body realizes, oh, the pressure is less here. I don't need as much. So I'm going to get rid of this excess internal pressure and I'm going to equalize what's around me. So it's, if you've got a dive and the dive is going to last an hour, you might only get 20 minutes to look at things at wherever it is that you're trying to get down to, because it's going to take you 20 minutes to get down and another 20 minutes to get back up. Let's talk a little bit about some real world gas pressure stuff. So give myself a little bit more space. I'm going to start off with an airplane wing. So how does this apply to an airplane wing? This is what airplane wings look like. This is what kites look like. This is what the new, I don't even know what those things are called. Wings, the thing that people just actually hold on to. Looks like a kite, but doesn't have any lines. And then this is what bird wings look like. So what happens? Well, the plane is traveling in this direction. Okay, so I've got some air here. the plane is going to travel through this air. Okay, so when it cuts through this air particle, these air particles here that it's passing through have a straight shot to the back of the wing. These air particles do not. These air particles have to meet at this same spot at the same time. So how does that work? When the top air particles have to go a farther distance, that means the top particles have to move faster. So if I've got to go this far and you only have to go this far, I have to be moving faster. And since I'm moving faster, my ability to hit the top of the wing is less than yours because you have more time to spend next to the wing. This is what provides lift for the airplane. So the faster the plane goes, the more that this wing acts like a wing. So literally quicker, at some point, the plane lifts off depending on what its weight is and the size of its wings, but it has to attain that flight speed, that minimum speed to allow lift to cause air pressure to push on the bottom of the wing harder than air pressure pushing on the top of the wing. That's it. That's Bernoulli's principle. That's how flight happens for anything. Same thing even with a helicopter. It's just that its wings, the wing things are those blades. All right, I'm going to erase this. I'm going to talk about one other thing. All right, so all right, so here's a baseball. Let's say the baseball is traveling that direction. Okay, so the ball is going to tumble as it's going through. So let's say that this ball is tumbling in this direction. When it tumbles like that, it actually produces its own little air currents around it. The air will actually, right against the ball, will be hit by the ball, and then these air particles will spin with the ball like a fan, a really bad fan, but regardless, it does produce this little field of air around the baseball that's traveling in the same direction that the baseball is traveling. Okay, so, or traveling in the same direction that the ball is spinning. Alrighty, so what about these air particles here that it's running into? So as the ball travels through and hits these air particles, it's trying to get through them. These air particles, sorry, I'll do that. I'm just gonna undo. These air particles on the top part of the ball, they are pushing against these air particles on the top of that are around the ball. And then these air particles here are going in the same direction as the air particles that are really close to the ball. So what ends up happening is the top of the ball, this is slow air. And the bottom of the ball, this is faster air because they're traveling in the same direction. These guys are running into each other on top, slowing everything down. So because they're moving slower, the air particles on the top of the ball hit the ball more often than the air particles on the bottom of the ball. So what is this ball going to do as it comes towards the plate? It's going to dip. So that's if the ball is traveling in that direction, but if it's perfectly rolling over the top. But what if the ball instead, I'll draw another one. What if the ball is kind of spinning like this? Then the ball will actually cause, it'll be, it's actually not going to happen. Say the ball is spinning like that. Then over here, and it's traveling away from us, then we're going to have slow here and fast here, and this ball is going to sink this direction. So depending on how it comes out of the pitcher's hand, the ball, for baseballs, the ball is going to go that direction or any angle below. The ball doesn't go up for baseball. So as the pitcher throws, the batter has to think about two things. Where's the ball going to be, and when's the ball going to be there? So a pitcher will change up his speed. He doesn't throw as fast as he possibly can every single time, because then the batter will get the timing down and then just have to worry about position. So you vary your speed and you vary your location and you vary how the ball travels there. So depending on how the ball is coming at you, you will actually see some dots on the baseball. What I mean by that is if an object is spinning really tightly, then let's say it's spinning this direction. This right here is going to look like a dot. The rest of it's going to be a blur. So depending on how many dots the ball has as it's coming towards you, that will let the batter know. And they've got a split second to see this and understand that the ball will be going down, or down and away, or down towards them. And so they can adjust where they're going to swing the bat. Softball is a lot harder, though. Softball is a much harder sport for batters because in softball, you have another factor. In softball, the ball doesn't just spin this direction as it's going. The ball can spin the opposite direction because depending on how the softball pitcher releases the ball could rise. That's not something that happens in baseball unless you have like a submarine pitcher, but that's an unusual pitching style. So softball batters have a much more difficult time for two reasons. One, the pitcher is closer, a third closer, 45 versus 66.6. And the ball can go up any direction and up, so that the entire spectrum of direction around the plate. And so usually when you see like the women's female Olympic pitchers pitching against a baseball player, like an all-star baseball player, the baseball players aren't willing to do that very often because they get humiliated. They get struck out by those female softball players. Even though the ball's bigger, you never know where it's coming from. You never know where it's going to because it can turn in any direction. Okay. Let's talk about Evangelista Torricelli's barometer. So this is his barometer here on the right. What we've got is a tube, and this tube is a glass tube. Make this a little higher. That's not at all what I wanted to do. Right there. Okay. So it looks like a really tall, skinny test tube. And he fills the test tube all the way up to the top with mercury. And then he takes the tube, puts his thumb over the top, and puts his thumb down into a dish that's filled with mercury. Obviously not good. Hopefully he's wearing gloves, but I'm sure he wasn't at that time because they didn't realize mercury was a problem. They actually used to drink mercury to cure, say, syphilis and tuberculosis, which is obviously terrible since it's a poison. So yeah, we get smarter, hopefully. Okay, so what happens to this when you turn this tube upside down? The height of the mercury drops because of gravity trying to pull the mercury down. But because atmospheric pressure is pushing down on the top of this mercury dish, it's forcing the mercury to stay up there. Okay, so this is a device to measure atmospheric pressure, and the height of the mercury is directly correlated to the actual atmospheric pressure. The higher the pressure, the higher the mercury will go because you've got more air particles beating down on the surface versus if there's less air pressure. So if you take this up to Denver, there's less air there. So this thing would fall because there's less particles of air pushing down on the surface. If I take it to Death Valley, it's going to rise because Death Valley is below sea level and there would be more air there pushing down on it. Also, if it's cold, then the mercury wouldn't rise as much because the air particles aren't moving as fast. Okay, so why is this important? Well, it's important because Torricelli was trying to study atmosphere, but he was also trying to determine how atmospheric pressure relates to weather. And so this is an interesting phenomenon. We still use this today. So let me get some space here. So, bad drawing. Washington, Oregon, California. If it's like Thursday and you're looking at the weather report and you see a big old H out here over the Pacific Ocean, what's that mean to you? So the H means high pressure. All right, great. So what's high pressure mean? High pressure means that if I put a barometer down, in this case, out in the middle of the ocean, they've got weather balloons measuring air pressure. And so how do you get high air pressure? So if I've got this barometer, I have air coming down from the upper atmosphere, beating down on this barometer. Okay, so the air pressure is higher because the air is coming down. How does that affect weather? Well, in the upper atmosphere, so if we've got Earth, we've got this atmosphere out here. Up here, it's cold. And because it's cold, the air is cold, the air is dry. So even though the air that's coming down, providing this high pressure, is cold, as it gets closer to the surface of the planet, it warms up. That's not the important part. The important part is it shows up dry. That's the reason you need chapstick when you go skiing, because the air in a cold atmosphere has very little moisture in it. So the moisture in your lips gets sucked out of your lips, causing your lips to chap. So if I see that big H out there, what I'm understanding is that is going to blow over Oregon. And then I'm going to have air that's coming from the upper atmosphere that will be cold, yet free of moisture, which means I'll have no weather that weekend. But on the other hand, if the air is coming from the Earth, we would have a big old L out here. So what does that mean? Well, what's on the surface of the Earth? Water. And as the air evaporates, it doesn't just, as the air moves up, water is going with it. So as that air goes up, it's warm down here. And as the air climbs, it gets colder. And as it gets colder, it coalesces into drops and then falls back down on us as rain. And so I would know that I'm going to have a potentially rainy day or rainy weekend because there would be less air pressure pushing down on this, which means the air is leaving the surface of the planet and taking moisture with it. And so that's going to come down on me. For us, where we are in the gorge, Cascade Locks gets beat with a lot of it because those clouds try to climb over the mountain. And as they climb over the mountains, as they reach a higher elevation, it gets even colder because they're further away from the surface of the earth. And then that it rains. So Cascade Locks is one of the rainiest parts of the country, simply because of its position and it's where it's sandwiched between multiple mountains. And obviously, as you go further and further west, it gets more dry because the rain is spent before it can get to, say, Pendleton. Okay, so there's Evangelista's barometer and how that barometer works. If you're watching the weather report, you might see something like barometric pressure is 31.5 and millimeters of mercury and rising. So to me, that would be like, okay, it's going up. So it's probably going to be a better weather. That's a way to check that if the barometer is going up or down. That's telling you if the weather is going to disappear or if you're going to have more. This next part is the units for gases. And I can't do anything other than to apologize for the fact that there are a bunch of them, but there are. So there's torricelli's, which obviously named after Torricelli. And the Torricelli and the millimeters of mercury are equal to each other. So we started off with millimeters of mercury. That's what Torricelli was calling it because he was literally measuring the height of his column with millimeters. And then after he passed away, they decided to rename that Tor in his honor. So torrs and millimeters of mercury are identical to each other. Every one of these numbers is equal to all of the rest of the numbers in this table given its particular unit. So PSI is 14.7 and 760 millimeters of mercury. Those two things are equal to each other. They would, if I was using two different devices, they'd be measuring the exact same pressure. One would say 760, one would say 14.7. If I was using another device that measured in atmospheres, that would be 1 atmosphere. That's equal to all of those. I have no explanation for bars being 1.01, just what it is instead of it being 1. Kilopascals is actually the official unit for the metric system. It's not used as much as some of these other ones, but it is still used. And then inches of mercury, regular atmospheric pressure is 29.9. So 29.9 would be equal to 14.7 psi. And then if I was using a barometer made of water, which wouldn't be a good idea because the water would evaporate, I would constantly be having to add water to it. But the other problem is this darn thing is 33 feet tall. So I need a big ladder or attach it to a building and be able to look out the window to read it. The other problem with it is if it goes below freezing, then it freezes and now it doesn't work as a barometer. But I can figure out how much pressure is going to go up based off of my depth if I'm in, say, the ocean or a lake or something like that. Okay, so again, sorry about all these different units, but they all exist, and all of these units are equal to each other. So if you're given a gas pressure in torr and you're asked to calculate and then give a gas pressure in kilopascals, here's your conversion factor. 760 torr are exactly equal to 101.325 kilopascals. In the same way that 12 inches is equal to 1 foot. It's literally a conversion factor. All right, and that's all I've got for this video.